function represents taking a number at this node that's called the activation and propagating it to the next node, combining with a bunch of others. That's just a linear operator, right? So I have a matrix multiplication that goes from this layer to this layer. Then we pipe those things through a nonlinear function. You have to put some nonlinear into this or it's not going to be very interesting, right? If I just had a sequence of matrix multiplications, they amount to one big matrix multiplication, and that's not going to be a very interesting result. But instead, I can put some nonlinearities in applied to the output of each matrix multiplication at each layer. And that allows me to have some fun. It allows the fitting function that's described by this to be incredibly flexible. To know how well we're doing, we define this loss function J. And I'm only spending a moment on this because it's important that we can fix one part and take derivatives with respect to another part. Okay, when we train, we're looking for the parameters theta that describe the neural net. And we've got some training data. We've got inputs X and outputs Y. So image of cat and cat. And we are looking for the thetas that minimize the loss function for fixed X and Y. When we're trying to, which is what I say here, when we're trying to attack a neural net later, we have a fixed neural net. It's already been trained. It's done. Theta's fixed. And now we're looking for inputs that fool it. So now we take derivatives of J with respect to X. So J is this really, really complicated function, right? This might be 100 million dimensional. That might be a million dimensions. It's such a complicated function, it can be a little hard to think of, but if you just break it down to a simple example and think about toy problems, it makes a lot of sense. So ideally, if things are working well, we can have some image, throw it at the neural net, and an output stop sign. One way to think about what it's doing is, as you go through these layers, so that little figure I showed you was what's called a fully connected neural net, where every node knows about all of the nodes in the layer before it. In practice, that's not always the best way to do things. If you're just trying to find edges in an image, you only care about a small region, 3 by 3 pixels or maybe 5 by 5, and you can find an edge in that region. So it makes sense to have convolutional filters that you sort of think about passing over the image. And those filters might look like these. You know, these are detecting edges at different angles, things like that. And that of course is just a simplified case of the previous one. You can still phrase this all as matrix multiplications. It's just the matrices get very sparse if you're doing it this way. Then out of such layers, you can build more complicated things. This is layer 2, it's probably actually layer 5 or 10, but you start to see eyeballs and noses and things like that. And then you can build, out of those pieces, you can build things that look like faces, for example. So the way to think of these layers of a neural net is that they're increasing their level of abstraction. So they're starting in a pixel space, and then they're going through many, possibly many, many layers of abstraction to get up to things that represent what we're actually interested in.
How do you do that actually?
You fit a 100 million dimensional fitting function in. I mean, it's, how indeed. And it's worse than I've made it look. Because I showed you just a nice little diagram with a few connected things. This is the venerable old Inception version 3 from a few years ago. This is a diagram of the whole neural net architecture. I'm going to zoom in on a little piece of it here. And each of these boxes represents a convolution by some kernel, taking the output of the previous layer and going to the next. Each of the red boxes. They also do things like pooling. You can bin the result down. You can renormalize it. There are other things you do, but every red box is a convolution that represents probably millions of operations.
Orchestra leader that's determining what you need at each stage in order to get the end result.
Not really. That's the amazing thing. You throw a million images, a million samples from the distribution you're trying to mimic at it, and then you cycle through a very large number of times optimizing the parameters of the fitting function. And it just finds a representation that works. It's really shocking that this works. Yes?
What I don't get is the parameters. Where are the possible parameters coming from?
So you
Things that it's trying to fit.
You start with noise, right? Inception v3 has 24 million parameters, so you assign the 24 million numbers randomly. And so your first few iterations are outputting garbage, but it's following a gradient in that 24 million dimensional space, looking for a place to minimize the loss function. And it takes a lot of steps to find it. And there are a lot of false minima to get stuck in. So you do stochastic gradient descent, where you effectively add a lot of noise to that process by only considering a small number of the samples at each training cycle, and you loop through. And so you're kind of getting pushed around in this very stochastic way in the space, and then eventually settle on something.
Can you please go ahead? So can you start with some guess? I mean, let's suppose that you have you know the image, right? But then if you start with a guess that is not exactly that, but it's randomized around the guess, then instead of 24 million, maybe you can reduce it substantially, right?
Yeah, so actually some version of that a lot of people do is to say the first few layers of this are just finding convolutional filters that detect edges and corners and simple things. And those are going to be the same just about independent of what images you're interested in. You have to find edges. And so what people will often do is they'll pull something like this from GitHub that's already been trained, and they'll say, I'm going to take these 10 million parameters here and just fix them to what Inception v3 already got. And I'm only going to let these parameters float. And then you train much faster. So that's called transfer learning if you're taking a previously trained neural net and then perturbing it to do something new. That's transfer learning, and there's a lot of work on that. Sorry, Charlie.
I think Paul's question was, what's actually being parameterized? You haven't really described, like, what are the actual parameters?
So the parameters may describe these convolutional filters, right, that look like this. Okay, so these are just pixelized, and these are bigger than they should be. 5 by 5 is the biggest anyone ever actually uses. So you have 25 numbers. That's a convolutional filter you can convolve your image with. And if it's set to detect edges at a 45-degree angle, that's what it does. And then you have maybe 100 of these, something of order 100. And so now you have 100 filterings of your image. You do that, you bin them all down, then you put them through the next filter, bin them down, keep going. So what filters to use at each stage, and then what the connections between the outputs of that filtering and, because you can filter your image with something like this, so now you have a number for every pixel of the original image. Those are all going to feed into the next stage, but in a linear combination with the outputs of all the other filters. Then that linear combination goes into a nonlinear function, and you go to the next thing. So there are lots of numbers here. There's the filter weights, and then the weights that connect those to the next layer. Yep.
Is one of the reasons why the training data sets have to be so large, because there are redundancies among the images, and if we were to find the most dislike images to form maybe a basis or some set of principal component images, I know this has been done with faces, they would reduce the number of inputs greatly.
Yeah, conceivably. I mean, there's a strong sense that there are a lot more parameters here than should be necessary, and a lot more training data than should be necessary. And there's work on that maybe I'll come to about how to regularize these better and help them generalize better. Yeah, one more question that I should do, because I think I'm going to address some of these things as I go on.
Do you need specialized hardware for this? Could you run it on a PC, presumably slowly?
You can run it on a PC. A lot of what's going on here is matrix multiplication, and the CPU cores, like the Skylake cores, can do 192 operations per nanosecond per core. So that adds up. But GPUs are good for this, and Google has some custom designed hardware that's effectively a GPU but highly optimized for these calculations. Let me plow ahead. The image classification success rate has gotten better over the years, to the point where they discontinued the main competition for that in 2017 because it's not interesting anymore. Did you realize that? It's not interesting anymore. the localizing the objects in an image is actually a harder problem. The performance has lagged on that, because it's actually somewhat hard to say that's a bird that has a frog in its mouth. You know, that kind of contextual thing. You know, this is a person on a motorcycle in front of a car and so on, wearing a helmet. So that's not a completely solved problem yet, but there's been a huge amount of work and it's going pretty well. I just wanted to point out that these things are not translationally invariant. You might think, oh, convolutional neural net, that's great. I can take my object and shift it over by a pixel and I'll get exactly the same answer, because it's all just convolutions anyway. But it's convolutions followed by these, you know, binnings and so on. And so exactly how you hit those binnings can change the answer. So there are examples. It's uncommon, but you can construct examples where you classify an image correctly, move it a pixel to the right, and now it's totally wrong. So that's alarming. I'm going to start telling you alarming things. Because, you know, despite all these successes, these machine learning models, and deep neural nets in particular, are fragile. They're only as good as their training data, and that's seldom good enough. They're very high dimensional and opaque, so we have trouble figuring out what they've actually learned. And so for those reasons, the model design and optimization is really an art. When you talk about people who do this for a living, there's, oh, well, it doesn't work. Well, add some more layers. Well, I don't know, try a different activation function in layer 13. Well, maybe we should try, you know, a different temperature on the softmax output. And they turn all these knobs, and finally they get something they're happy with. This is extremely unsatisfying to a physicist. About 4 years ago, so Szigeti did this first, I think, but Goodfellow wrote a very nice paper on turning a panda into a gibbon.